Okay, it's a great pleasure to introduce to Irina Markina for this next session of the virtual seminar of geometry with symmetries. She will talk about a unified approach to extremal curves on Stiefel manifold. Thank you, Irina.
Thank you. Thank you for invitation. And thank you for keeping the seminars for the people from all over the world. It is funny to say, yesterday I told to my student that tomorrow I have to give a talk in Argentina. And he was like, how? You will jump to the airplane and fly? Oh, no, of course not. Yes, this is advantage. So now about the talk, this is a joint work with two collaborators, Knut Hueper from the University of Wurzburg, Germany, and Fatima Silva Leite from the University of Coimbra, Portugal. They are collaborator for the long time, and I, in a sense, joined their team. And they are more from applied mathematics from the pure, so that was interesting work together. And I will talk about, will tell you the story about these things. So Stiefel manifold, just to remind you, what is the Stiefel manifold? Is just a set of K, and I will think that they are orthonormal, linear independent vectors. So orthonormal, of course, linearly independent. So in our case, we will be working with the space with indefinite scalar product. Yes. And to simplify the discussion, I will assume that V is just a vector space, and this is just Rn, and it's endowed with the Euclidean product. Yes, with Euclidean product. And the Stiefel manifolds are named after the Eduard Stiefel, and that published this paper in the Commentaries of Mathematical Helvetica, and essentially it's results of his thesis, the direction fields and the teleparallelism in n-dimensional manifolds. So you have the German name and the English translation. And his this thesis was written by him under the supervision of Heinz Hopf in Zurich. Okay. And if you look for the references, if you just Google for the words Stiefel manifolds, then it comes around 16,000 references in Google Scholar. So I just copy pasted some of them. So I just want to say that this is popular topic in applied mathematics and in pure mathematics, and therefore somehow partially my collaborators, they were working in some questions related to the Stiefel manifolds, and therefore somehow this topic came to the discussion. Okay, so let me define Stiefel in a different way, and then I will show you, we'll choose one model in which we will be working, and then somehow this model include all of these look like different approaches, but they unified in one, and therefore it's called unified approach. Okay, the Stiefel manifold can be considered as a set of matrices, n by k matrices, such that the columns and columns, they are orthonormal. The orthonormality is encoded in this equation. So we can think about Stiefel manifold as embedded into this vector space of the matrices, and it's possible to calculate the tangent space at x. X is element in the Stiefel manifold, so it's satisfied to that condition. And the tangent space can be described as a set of matrices that satisfy this condition. And okay, you sit down and calculate that. You take whatever matrix, and then you project from this vector space, from ambient vector space to the tangent space to the Stiefel manifold, and this is the formula where you see the x is the point where you have the tangent space, Z prime, the original matrix, and yeah, so it satisfies to that one, and it will be skew symmetric matrix or element of S or of the dimension K. Of course, you can describe this manifold, the Stiefel manifold, as the pre-image of the point of the map F. So if you defined a map from F to the space of symmetric matrices, so the matrix is defined by this one. So for any X, we associate this matrix, and then the X is just pre-image of the identity matrix. So the element in the Stiefel manifold belongs to the Stiefel manifold. X matrix belongs to the Stiefel manifold if X transpose X is equal to identity. So the Stiefel manifold is just a level set of the identity under this map F. So this is some other point of view that we will be exploding in one moment. And then now the vector space M can be endowed with the rather standard metric that in literature people call it Frobenius inner product. It's just a trace of this x1, x2 transposed. Yeah. And then this metric, this scalar product, inner product or scalar product, it's induced Riemannian metric on the Stiefel manifold, yeah, that embedded into the space of the matrix. Another approach that quite often used in the literature to work with the Stiefel manifold is homogeneous version. So first, it's defined the action of the group on the manifold, on the Stiefel manifold, on the set of matrices by the multiplication from the left. Yes, so from the right, from the left. Yes. So the matrix, orthogonal matrix, multiplied by the by this matrix in the Stiefel manifold, and then we can find the isotropy group of stabilizer of some point, yes, stabilizer on some point, and then Stiefel manifold will be diffeomorphic to that homogeneous manifold, where the stabilizer is isomorphic to the orthogonal transformations of the dimension n minus k. This is one version of the homogeneous manifold that used in the literature. Another one, it's quite often consider another action, different action on the same set is the action of the product of the two orthogonal groups of size n and size k. So these two elements of the group multiplied from one side or from the other side, V transposed. So this is we need in order to, let's say, make the size of the matrices correct. And then again we define the isotropy group, the same story, define the isotropy group, but the action is slightly different. And then we can consider the factor of this bigger group by the isotropy subgroup, where the isotropy subgroup will be in this case isomorphic to this direct product of the orthogonal transformations n minus k by the k. So in both cases, the idea is the same. We just change the action, the group, and change, of course, the isotropy subgroup, but the same, the Stiefel manifold can be considered as a different homogeneous spaces. Now that was the manifold picture, and now we would like to look on the Stiefel manifolds as on the Riemannian manifolds. I already mentioned that one of the approaches just restrict the Frobenius inner product from the space, from this vector space to the embedded manifold, and consider this like Riemannian manifold. But when we have the homogeneous version of the Stiefel manifold, then it's worth to consider some invariant under the action of the group metric. Yes, and this is of course also given by the trace metric on the Lie algebra of the group. Yeah, but if if we are working on the homogeneous manifold where the group S or N times S or K acting, then in our approach, we decided to consider this kind of metric. So this is the metric that will be bi-invariant, and this is defined on the product of the Lie algebras, SON small, SOK. Yeah, so we take two vectors and then we calculate the trace between the elements in SON and then trace between the elements in SOK. And actually we wanted to consider the family of that matrix. So we just started from the considering the linear combination of that metric and that metric, but then we normalized, and then it's essentially one parametric family of the matrix. Actually one parametric family of indefinite products on the Lie algebra of that group that consists of the product of two orthogonal groups. Yeah, so this is just this linear combination with alpha. Of course, alpha here is not equal to 0 originally, but eventually in one moment I will explain that even for alpha is equal to 0, it has sense. But this is indefinite product. It's not positive definite, it's indefinite. And it's need to consider also the cases when it is degenerate and, or when it is non-degenerate. Yeah, but this is a B-invariant pseudo-Riemannian. Pseudo-Riemannian, it means that this is not positive definite, not positive definite. So on the group that acts on the Stiefel manifold, we define this pseudo-Riemannian bi-invariant metric by the translation of this, by the left translation of this one, but since it is a joint invariant, we will get to the bi-invariant metric on the group. Yes.
I am missing something. Can
Yes.
you show please the previous slide? For alpha equal to 1, for instance. No, the next one. For
Alpha is
equal to, yes. This is the killing metric, right? The standard metric of the
yes,
of the
I will
product
come
of
to that.
these groups.
Yes, the
But
things is
I am missing something because I feel that this is a positive definite. And
for
is
some
it?
alpha is positive definite, for some alpha is non-positive definite.
Okay.
Alpha is
Thank
not
you.
equal to 0, since for alpha is equal to 0, you cannot define. And I will consider the particular cases. And you are right, for alpha is equal to 1, it's coincide with some standard metrics.
Okay, thank you.
So, yeah, we have the action that I already mentioned. And then, as usual, if we fix point K and consider the stabilizer of that point, and we associate the Stiefel manifold as a homogeneous manifold, then the action of the group on the Stiefel is written in this way. And this map for any fixed X is just a submersion from one manifold to another. Submersion, as usual, this is a surjective map whose differential is also surjective. Yes, surjective. And then we decompose. So we fix X, yes, and we look on this submersion. We look on this submersion. So wait. We look on this submersion, and then we look on the differential of that submersion, that the identity of the group. So this is just a map from the Lie algebra to the tangent space at that fixed group. And here the relation between the two elements in the Lie algebra, that is always will be written as a pair because of this product, and the elements in the tangent space. So the psi, just remember, I will be interplaying between elements of the Lie algebra and the tangent vector to to the Stiefel manifold at this isotropy point, the fixed point. And since it is surjective map, since it is submersion, it is surjective map, then of course there is a kernel of that map. Yes, so this is exactly the map where omega x is equal to the x omega. So here you can think about about this property. This is the kernel, and the first statement that it's not difficult to see, but it's need to verify that this this metric that we defined here with alpha depending, it's non-degenerate if and only if alpha different from 1. So from -1. If alpha is equal to -1, then this metric is degenerate. But we would like to have the decomposition of this Lie algebra into the orthogonal subspaces with respect of that indefinite metric. And it is known that it's possible to get from the kernel to the orthogonal complement to the kernel orthogonal in a full sense if the metric is non-degenerate. So therefore, we exclude alpha equal to -1, but for all others alpha, of course, alpha is not 0 yet. So of course, because it cannot be written, cannot be calculated here. But for any alpha except of 0 and -1, this product is non-degenerate, and therefore we can find the true orthogonal complement to that V with respect of that indefinite metric. So and now we are coming to the standard situation when we have the decomposition into the vertical subspace that will be just a subalgebra, that is a subalgebra of this G, and the complementary subspace P that will be just reductive, will express the reductive properties of the Stiefel manifold, and also this is a little bit, I'm a little bit cheating. For any k, when dimension k is bigger than 2, yes, then we have also this property, and this property allow us to have a connectivity by curves that all the time will be somehow parallel or tangent to the distribution that we will be defining by left translation of this this complementary space P to the subalgebra, to the kernel. Okay, sometimes people say that this is non-integrability condition, sometimes bracket generating condition, and so on. There is different terms in the different companies, but it's very useful for us because we somehow will be talking about the curve connecting different point in tangent to this left invariant distribution. And okay, this is a job with the people from background from engineering or applied mathematics. They wanted to have all the formulas. The formulas also in the paper, and they are quite long, but here I would like to illustrate the standard situation. So when the isotropy point is this one that is usual choice and the most simple choice, then then any element in the Lie algebra of a group that acts on the Stiefel manifold can be written like in block forms. So the first one is element from the n-dimensional, not n-dimensional, but matrices n by n. We write in this way where B is just a matrix of this size, and A from S has A from S or K, and C, of course, from S or N minus K. So in these block forms, when we write omega in these block forms, then it's possible to write precisely the formula for the decomposition of that Lie algebra into the vertical space that is kernel of that submersion and the orthogonal complement. Since the orthogonal complement all the time calculated with respect of the alpha, so somehow it's alpha is present here and here, and you see already when it is calculated precisely, then you see that alpha is not equal to 1. is also, it's even here reflected that the problems appear when alpha is equal to -1. And we already removed this alpha is equal to -1 because we were looking for the true orthogonal complement for this vertical space. Okay, so, but then continuing the story, now we had a submersion, but we want to have the pseudo-Riemannian submersion. Yes, pseudo-Riemannian submersion, it's direct. So that was studied by O'Neill a lot. O'Neill, and it's very popular and well-known object. So in order to get to the pseudo-Riemannian submersion or Riemannian submersion, just meaning that our metric can be indefinite, we already constructed the vertical space and the orthogonal complement at the level of the Lie algebra, and then now we use left translation. Since we have this bi-invariant, we have the action of the group, we just translate this vertical and horizontal, we get the vertical and horizontal distributions. And then this scheme, when the G acts on the Stiefel and the left translations on the G go to the change of the point from leads to the action on the Stiefel manifold at the level of the infinitesimal level, at the level of the Lie algebras. So we have the isomorphism between this P space that is orthogonal complement to the kernel. Yes, the isomorphism between P and tangent space at the isotropy point. And then the left translation give us the value, the distributions at point G. And then by the differential of this action coming at point G, we come to the tangent space at any moved point, yeah, from the isotropy point to any other point. Okay, standard scheme. And this is just reminding of our action, but we want to define the metric. Okay, the same picture, but we want to define the metric on the Stiefel in such a way that under the pullback of that metric from the Stiefel manifold from any point to the group G, and then projecting to the horizontal distribution, we get to our metric that is a bi-invariant metric. So this metric is given. Not given, but we choose it to be bi-invariant metric from this one parametric family on the Lie algebra. Yeah, and then we just project it to the H, and we want to define the metric on the Stiefel manifold such that its pullback coincide with the given metric. Okay, some job, some calculations. And then, okay, so this is the relation that reflect the pullback property, where now we have calculating only the trace product between the element in the Lie algebra that belongs to the horizontal space at the identity. Yes, so, but for that, one sit down and calculate the relation between the projection to the horizontal space at the level of the Lie algebra and the elements of the tangent space. So the xi is the vector tangent to the Stiefel manifold. Yes, and this is the relation between the element in the Lie algebra and the tangent vector. So for the omega part, it's a little bit longer, but x is the isotropy point. So this is more or less general picture. And then if we just plug in this kind of projections that calculated here, we get to that metric. But now xi1, xi2, this is not element of the Lie algebra. This is now the tangent vectors at points at the Stiefel manifolds. Yes, and they are related by this formula. And again, you see that alpha is equal to -1. For alpha is equal to -1, this is not defined. This is not well defined. But for alpha is equal to 0 now, it has, in a sense, has full sense. But we will discuss about this. And now the particular cases, as already was mentioned, that for alpha is equal to 1, with this isotropy point, the standard isotropy point, we just recover this this kind of metric, and this is corresponds to this metric, this trace metric, yeah. So this situation was considered, for example, in the papers of Fedorov, Jovanik, and by Anthony Bloch with the co-authors. And the decomposition, so this is the, again, Bloch form of the elements from the Lie algebra, and the horizontal space has this form, where A and B from this decomposition, and psi is the element, any other element. Yeah, so this was known. Then for alpha is equal to -12, we recover for alpha is equal to -12 for the same isotropy point. That how look like metric, and this is just a metric that coincide with the up to the multiple 2 coincide with the metric that comes from the embedding of the Stiefel manifold to the vector space of matrices. So in that one parametric family, this kind of Riemannian embedding is also considered, but the space P have different form. So essentially what we are playing with the different, depending on alpha, we get some metric, and of course orthogonal complement to the kernel is changed, and therefore the P is changed. We have different forms of P, and that work was considered, so that metric, for example, was considered by co-authors by Knut with his collaborators and Fatima in different papers. Then if
Irina,
alpha, yes.
One small question. This metric, alpha equal to -1/2, is this metric the killing or standard metric of the
Frobenius
other
metric.
action, the ON?
No, I will come to that. It's Frobenius metric in this case. When alpha is equal to -12, it's Frobenius. Is the metric that obtains by restriction from the matrices n by k to the Stiefel manifold.
Okay, but I thought that also coincide with the other one.
No, it's different.
Different. With the other action, ON, only ON.
I will come to that. That metric will be obtained for alpha is equal to 0. So,
nice. Okay.
Yes. I'm going to that. So alpha 1 is known metric was for alpha is equal to 1, it was known. For alpha is equal to -1/2, it was known. Now for alpha is equal to the infinity. Yes, because if alpha is equal to the infinity, then this metric, if we recalculate, then this will be that metric, and this is not the action ON. This is again the action ON cross OM. The horizontal space now has this form, and that was considered by these co-authors. And originally, it's a peer. Maybe it was in the different sources, but where I learned it from Fatima, when she with some of the other people were looking for them. They were trying to calculate or construct the splines on the Stiefel manifold. So how you can define the polynomials of order 3 on the Stiefel manifolds, and they considered different constructions. And one of the constructions, it was a process involving the projection from the Stiefel to the Grassmann manifold and going back and so on. And that was very interesting combination. So they had metric that is here and the P that is here, but they come to that situation absolutely by playing with trying different approaches. But apparently here we recovered again the approach with concrete alpha, and for that alpha we get the P. But they came to that situation from completely trying different possibilities. And now the alpha is equal to 0. So originally this is the definition, and alpha is equal to 0. It's not. It's look like is not defined. But then what if we try to calculate what's happened with this expression when alpha is going to 0? Then let's look on the intuitively, it has to have some limit. Why we expected that limit exists? Because I recall you that if we write the metric not in the Lie algebra, but on the tangent vectors, yes, in the sense of the tangent vectors to the Stiefel manifold, then we come to that kind of expression. And for that kind of expression, alpha limit when alpha go to 0 has a perfect sense. So therefore, we is just need to explain the limit on the level of the Lie algebras in order to smoothly glue together these things. And now, and this is another observation. So if we write the projection to the horizontal parts, to the horizontal part of the Lie algebra, then it has this form. And here also, when alpha go to 0, we see that it's converge to this kind of distribution. And see here, it's already also there somehow intuitively clear that since in the limit the p part has the second component that correspond to the SOK 0, then it somehow give the idea that the action here is only by the group ON, and OK here will not play important role. Yeah, so but this is intuitive description, but if we go in a little bit more careful calculations, then we can see. So this is the formula for the projection of part of the psi from OK. Psi belongs to OK. So this is in the SO small k. Yes, and here, yeah, so the psi is the tangent vector here. And then I just write this formula in this way, 1 over alpha psi, and here I keep so I divide both part by 1 over alpha. And now we see that when alpha go to 0, then somehow this expression or these projections is going to that one, because this we have limit of that part. So when alpha going to 0, then this kind of the projection vector is go to that one. So it has sense. Therefore, in this metric, we just using the linearity property of the trace metric, we just put 1 over alpha here, divide by 1 over alpha and multiply by 1 over alpha. But now when we take alpha go to 0, each of these vectors, they have limit, this one. Yes, and therefore trace has a finite limit, and when alpha go to 0, we actually see that this is go to 0. So in this trace metric with alpha go to 0, when alpha go to 0, the second part disappear, and the only important part became the metric in ON, in the first component. So the second component plays no role. Yes, as I already mentioned, the horizontal projection to the horizontal part is also has only the first part present. The second is 0, but then it's still there is dependence on psi. And to remove the dependence on psi, we just check the orthogonality condition between V and H, and this is immediately give us that A minus psi is equal to 0, and we come to the horizontal distribution that depends only on B, and does not depend on psi, where psi was element from OK. Everything depends only on the matrices A, B, and that from the first component, that is in SON. So this case, finally, this case when alpha is equal to 0 is reduced to the action of only one component ON on that manifold. This is exactly the answer that has the answer to the question. In this case, omega is just skew-symmetric matrix that written in this block diagonal form. This is from SOK. This is the complement part and so on. And the horizontal distribution is presented by this of diagonal matrices. So that is, let's say, this kind of approach, for example, can be found in this paper that people in engineering and applied mathematics used a lot this metrics, this kind of approaches, decompositions, and so on. But this is just a particular case inside of this one parametric family of metrics. And another things that using this one parametric family of metrics, it's possible to write some sort of Euler-Langrange equations describing the critical points of the energy functional and energy functional. So we change from this approach of the homogeneous spaces to the embedded manifold. So take the metric that we defined on the Stiefel manifold and extend it straightforward to any xi1, xi2, any matrix n times k. And we consider this kind of straightforward extension of one parametric family of the metrics for any, now this is just the matrices from the, okay, formally from the tangent space to the, in this vector space, but we can associate it with the matrices, n minus k matrices. And then the energy functional, or let's say Lagrangian, Lagrangian can be considered like this one. We would like to minimize the functional that has element in the vector space, has element matrix S. It's like matrix value Lagrange multiplier. So it's belong to the symmetric space. And what we minimize the length of the curve in the space of the matrices, yes, in our vector space. And we also minimize the, let's say, the closeness of the X to the, to be, so this part is force the curve X or whatever matrices our from the space to the space of the when this is became zero, and we remember when this is became zero, we exactly end up on the Stiefel manifolds. So it's minimizing of the velocity part, and this is like holonomic constraint that essentially push the matrix to belong from the space of the matrices to the Stiefel manifold, And then somehow the standard variational approach gives to this kind of terrible equation, But what is interesting, it could be written in a nicer form. As mathematicians, we like to write something in a beautiful form, and playing with the situation that x of t is actually the solution have to belong to the Stiefel manifold of that variational problem. And the derivative is just the element in the tangent space at each point, and then playing with the fact that we know what is the horizontal projection, and the horizontal projection exactly have to coincide with this element, with this velocity participating in this equation. So somehow one can find that this object, this kind of action of psi and psi on x does not depend on t for any, so it gives the same value as if we just took the value of omega and psi at initial point. So if we write like this one, the action of the, so essentially it's like initial velocity, then this equation can be written in a nice form, in this closed form, and this is the solution. Okay, it doesn't mean that we solve this equation. Of course, we knew this equation, because what we are looking for the geodesic on the Stiefel manifold. All this variational problem is just formulation of the problem to find the geodesic on the Stiefel manifold. And it was considered in a different literature and so on. But here we just wrote this variational equation or second order equation for the curve or with respect of any alpha metric. for any alpha metric that I remind you include several possibilities of considering different metrics with different realization that suitable for different realizations and so on. And here, like one equation, one system of the equation and solution written in this form. But it's not easy to solve this equation because it's matrix equation and so on. But it's just a checking the following, that yeah, no, do not be scared. That this is actually the different form of the projection of sub-Riemannian geodesic, correctly chosen sub-Riemannian geodesics from this group to the Stiefel manifold. So here I again glue two approach. So this how look like solution of that variational equation to find the shortest curve on the Stiefel manifold considered as submanifold of the vector space. And this can be done by a formula that can be found in several places. So it's well-known formula from the beginning of the last century or something like that in the control theory, and then it was generalized by Montgomery for the principal bundles. That essentially the idea is the following. So consider the Riemannian geodesics on the group, whatever group acting on your manifold, on your homogeneous manifold. So you consider the Riemannian metric, then you correct, but this Riemannian metric where the initial velocity is written like a sum in the horizontal part and in the vertical part. Yes, in the horizontal and the vertical, then correct with the multiplying by exponential minus t. Here we have the vertical part, and then translate to the initial point of that geodesic. So this is a very simple formula, and this is the general form of so-called normal sub-Riemannian geodesic. What is that? What does it mean, sub-Riemannian? It means that this is the shortest curve such that it's in any moment is tangent to the left invariant horizontal distribution that that is this one, that is orthogonal to the kernel of that projection and so on. And if we have this kind of curve, then it is sub-Riemannian. It's general form of the any geodesic shortest curve with respect of the metric that we obtain by the restrictions to the h, and this is in any point tangent to the horizontal distribution. Now, if the vertical u and up and ut, this is initial, the composition of the initial velocity vector into the vertical and horizontal part. Now, if from the very beginning this is 0, this is equal to 0. Yes, then we obtain the particular case of sub-Riemannian geodesic, but then projecting this to the homogeneous manifold, we come exactly to the Riemannian geodesic in the base space in the homogeneous manifold. And now if what we were doing is actually we were writing this kind of expression and then projecting it, we get to the solution of that equation. So now is just you take this expression, you put into the system of differential equation, and you check that this is satisfies, because we knew the solution. But in general, to solve it's not so easy. And what is more, yeah, this is just some small observation. This is written what I told you, and then what is also known that the geodesic curvature of the projection of this sub-Riemannian geodesic is equal exactly to the norm of the vertical part. So if vertical part is equal to 0, then we come to the Riemannian geodesic where the geodesic curvature on the base space, on the homogeneous manifold, will be equal to the 0. But yes, it's also the way how to construct. So using the sub-Riemannian geodesics on the group is also the way how to produce the curves of constant geodesic curvature on the homogeneous manifold. And it was exactly the main object that my co-authors were looking for when they were constructing spline on the Stiefel manifold. So the Stiefel manifold, for them, it's a homogeneous manifold. But they were not able to write nicely the geodesics, and they decided for the spline use not the geodesic connecting two points, because it was difficult for them to construct the geodesic connecting two points. But it was easier to connect these points by curves of constant geodesic curvature with the curvature that is not zero. So they call it quasi-geodesic. It's just because of the constant geodesic curvature. And they found these solutions, and they wrote this equation, but by several experiments and so on. But we came to this to the same conclusion for any alpha metric. But I remind you that for them, alpha was chosen infinity. When alpha is infinity, it's one of the examples in our case. And yeah. And particular case is just to mention that when the Stiefel manifold is n-1 dimensional sphere embedded into Rn, then the alpha metric actually does not depend on alpha. Does not for any alpha we have the same metric. And for the case when the Stiefel manifold is just the orthogonal group when k is equal to n, yeah, then we get that this alpha metric is nothing more than up to this constant that is any constant defined for any alpha is not equal to -1 that we excluded from the very beginning. This is also just a trace metric on the group. That on the Stiefel manifold, that is actually in this case it's a Lie group, and this is just a killing form. Yeah, up to the constant. Yeah, and yeah, essentially here the material from these papers that I used, and I mentioned several others that where there are some calculations. Yep. Wait, sorry. And this is the end of the story. Thank you for the attention. Now I can answer questions. Thank you.
Thank you very much, Irina, for the very nice talk. Are there any questions?
Everything was clear.
Yes, by the way, it was very clear. I have a question.
Okay, if I do not tell me that, how am I? How good am I?
Is there a chance to use any of the material here to find the diameter of any of this Stiefel manifold with some metric, not necessarily alpha equal to 0, which is most important?
It's interesting question. We never thought about this, but probably yes. I do not know. We never thought about this. We never asked this question ourselves.
Okay.
Sí, Irina.
Yes.
Hola.
Nice to see you. Hola.
Is for any alpha when you consider the B invariant inner product on the manifold, you got a non-degenerate. Is because the groups are of some special form, or because that's not a general thing for a homogeneous space, right? That that if you take a B invariant pseudo metric, you may define a pseudo metric on the homogeneous space, or it's general.
This is interesting question. We no, I don't think so. That this is, I do not know how to prove it for the general. If you have general manifold and then you start from the absolutely general pseudo-Riemannian metric, here the construction is pretty much particular. It's just a linear combination of two killing forms. Yes, and we just found that parameter where it's not degenerate. Okay, we exclude actually one parameter when it is degenerates. In all other cases, it was non-degenerate, but this is particular case, particular manifold and so on. In general, I do not know. Maybe Yuri Nikanorov knows. He's big specialist in homogeneous manifolds. Yeah.
Gracias.
Bienvenido.
Are there more questions? Okay, if not, we thank again to Irina.
Thank you. Thank you for invitation and have a nice day. You are in the morning. We are almost in the evening. Thank you very much. Then I stop to share.